welcome back after the short break. So, we are going to discuss about numerical example, and the circuit, it is still that equivalent circuit we do have, and what we are so we do have the generalized equivalent circuit, but then also we do have additional information, namely the value of different components. R 1, this input resistance is 1.3 k, then R 2 output resistance, it is a 3.3 k, and then let you consider source resistance 650 ohm, that is also a typical value, one possible value of typical signal source. And then the load capacitance C L 100 picofarad, C 1 it is given here, it is say 10 microfarad, and then C 3, which is one of the element contributing to input capacitance, it is say 10 picofarad. C 4, the Miller affected capacitance, the capacitor which is bridging the input and output terminal of the circuit is 5 picofarad. And let you consider this voltage gain A V or A naught, in this case. So, we are denoting this by A naught, which is a 240 with a minus sign. So, that means actually this is minus and this is plus. So, anyway, with this information, let you try to get the frequency response and particularly containing the mid frequency gain, and then lower cutoff frequency, and then upper cutoff frequency. So, how do we proceed? First of all, this resistance directly given there, but then we need to calculate the input capacitance. So, to start with, let you calculate C in, and C in equals to C 4 multiplied by 1 minus of 240, then plus C 3. So, we do have 5 here and then multiplied by 241 plus 10. So, that gives us how much? We do have 1 to 1 to 1 5 picofarad. Yes. So, we do have the C in is given here. With this C in, we can calculate the location of the second pole, and let we calculate the first pole first. So, P 1, which is defined by, if I express this in the unit of hertz, then we have to consider 2 pi. So, 2 pi multiplied by R s plus R 1 into C 1. So, this is equal to 1 by 44 by 7. C s it is 650, and then R 1 it is 1.3 k. So, that is 1950, that is the resistance, and then C 1 it is 10 microfarad, which means 10 to the power minus 5. And if you calculate it, I have done this calculation for you. So, what you will get, it is 8.16 hertz, right. So, you got the lower cutoff frequency is this one, and then we can get the second pole P 2, which is coming from again R s and R 1 in parallel, and since it is in hertz. So, we have to consider 2 pi. So, 2 pi R s in parallel with R 1 into C in. and the value of the C in it is given here. So, this becomes 1 by 44 divided by 7 into this resistance, these two resistances in parallel. So, we do have 650 and 1.3 K, it is coming close to 400. In fact, to be more precise, it is 433.3 ohm, and then C in it is 1215 into 10 to the power minus 12. And if you do this calculation, what you will be getting, it is close to 300, and to be more precise 302.4 kilohertz. So, we do have the second pole, it is given here 302 kilohertz. Now, you can also calculate the third pole P 3, which is coming from R 2 and then output resistance. So, P 3 it is 1 by 2 pi into R 2, it is 3.3 K. So, we do have 3300 ohms, and then output resistance, it is we do have CL equals to 100 picofarad, and then the C 4, it is almost coming as is. So, we can say roughly 105 picofarad, 10 to the power minus 12. So, if you do this calculation, what you will be getting, it is 459 in my calculation, that is what I obtained, 459 kilohertz. And as I said that since this is higher, so the upper cutoff frequency it will be decided by P 2, and lower cutoff frequency it will be coming from this one. And also to get the mid frequency gain, so mid frequency gain it is of course this multiplied by whatever the attenuation coming from these two elements. So, what is that attenuation? So, I should say V 1 divided by V in mid frequency range equals to R 1 divided by R s plus R 1, and R 1 it is 2.3, this is 0.65 kilo. So, that is equal to 2 by 3, and that gives us the overall gain. Let me use different color. So, overall gain A V overall. So, that is equal to 2/3 multiplied by 240 with a minus sign, and this is equal to 160, right. So, we should say that the overall frequency response of this circuit, it is something like this. So, I do have some space here. So, let me utilize this space. So, mid frequency gain it is given here, maybe we can convert that into dB, and then we do have the lower cutoff frequency here and then upper cutoff frequency. So, the lower cutoff frequency it is 8.16, and then the upper cutoff frequency it is this one, and this is because this is lower than the P 3 part. Okay. Now, let me go to one actual circuit. So, as I said that this is equivalent circuit, and of course, the value we have picked up here, it is very close to whatever the equivalent circuit we get out of actual circuit, but for you to get a feel of that, let me consider one practical circuit. So, in the next slide we do have CE amplifier, having fixed bias arrangement and different components of different components of these bias as well as the other value the capacitors and all, it is given here. So, RB it is 570 kilo ohm, supply voltage it is 12 volt, and then VBE on it is approximately 0.6. So, that gives the base current equals to 20 microampere. Earlier we have done this calculation, and with multiplying with beta we do get the collector current, it is 2 milliampere. Quiescent collector current is 2 milliampere. So, that gives us the GM equals to 2 milli divided by 26 millivolt. So, this is equal to 1 by 13 mho, and then R pi of the transistor, which is beta divided by GM. So, that is 100 divided by GM is 1 by 13, that means 13 into 100. So, that is equal to 1.3 kilo ohm. And then we have C1 it is given here. So, this is C1, C2 it is also equals to same 10 microfarad, and then we can connect a CL here, and this CL it is given equals to 100 picofarad. In addition to that, we are assuming that we do have a source resistance Rs to see the effect of this C pi and C mu. So, C pi it is given 10 picofarad, and then we do have the C mu, it is given as 5 picofarad. So, from that let we, and of course, the RC it is given here. So, from these parameters we can probably we can try to find the voltage gain, and then input capacitance, input resistance, and so and so. So, first of all, input resistance R in, which is equal to R B in parallel with the input resistance coming out of the device. So, that is R pi, and this is equal to 570 K in parallel with only 1.3 kilo ohm. So, you can approximate this by considering 1.3 kilo ohm it is dominating. So, that gives us the input resistance. Now, before we calculate the input capacitance, we need to know what will be the gain from this point to this point, and that gain, if I call say A naught equals to GM into RC, and so this is equal to 1 by 13 into 3.3 K 3300. So, that is becoming equal to close to whatever earlier we obtained or earlier we have taken, but to be more precise, I think it is 254, of course, with a minus sign. So, the voltage gain here it is minus 254, input resistance it is 1.3 K, and then we can calculate the input capacitance. C in equals to C pi as is plus 5 picofarad C mu into whatever 1 plus 254. So, if I put the value here, it is 10, and then value here it is 5. So, that gives us 10 plus 5 into 255. So, that is giving us 1285 picofarad capacitance. Okay. So, now we can calculate by considering this R s, we can calculate the pole, location of the pole. So, let you consider first pole P 1, which is equal to 1 by 2 pi into R s, which is 650 plus R in equals to 1300 multiplied by this C in C 1. In fact, this calculation we already have done for the previous example, and that gives us 8.16 hertz. On the other hand, we can calculate P 2. P 2 also it will be very similar. So, let me use this space here to calculate P 2. So, the expression of P 2 it is 1 by 2 pi 650 in parallel with 1300 multiplied by C in. So, that is 1285 picofarad 10 to the power minus 12. So, with this, so this is again this part it is coming whatever 433, and with that what we get, of course, this capacitance it is slightly different, and this gives us 286 kilohertz. Now, if I calculate the third pole, namely the pole coming from the output resistance, which is R c, and then the C L, and R c it is given here. So, the third pole, let me use this space to calculate the third pole, which is 1 by 2 pi into output resistance, which is R c, and then output capacitance, which is 100, and then also C mu coming there. So, that is 105 picofarad. In fact, if we calculate this, what we can get by putting the value of this R c equals to 459 kilohertz. Now, if I compare the P 2 and P 3, since P 2 it is lower. So, P 2 defines the upper cutoff frequency F u, and then of course, P 1 it is defining the lower cutoff frequency F L, and then the gain, overall gain, of course, it will be this multiplied by whatever the attenuation coming out of R s and R in. So, the overall gain A V overall equals to, so this is equal to 1.3 divided by 1.3 plus 0.65, in fact, that is 2/3 multiplied by this 254, of course, with a minus sign, and that is becoming close to minus 169, right. So, in summary, the mid frequency gain it is 169, lower cutoff frequency it is 8.16 hertz, and then upper cutoff frequency it is 286. So, that is the overall frequency response of the common emitter amplifier given here. Okay. Now, we can similar kind of exercise you can try for common source amplifier. Okay. So, again this circuit it is very similar, but we need to be careful here that GM of this transistor, MOS transistor, since it is much lower than GM of BJT. So, we are expecting the gain here it will be much lower, and then we can see what is its consequence in the frequency response. So, here we do have the value of different bias elements, namely R1 and R2s are given here, 9K and 3K respectively. We do have the supply voltage 12 volt, and then for this device parameters are given here, namely transconductance factor it is 1 milliampere per volt square, threshold voltage it is 1 volt, and then RD the passive load it is 3K. Now, if I analyze say this part to find the voltage here, since it is 9 and since it is 3, the voltage coming here it is 3 volt from this 12 volt, right. And once we have the gate voltage 3 volt and threshold voltage is 1, then we can say that this IDS equals to this 1 milliampere per volt square by 2 into 3 minus 1 VGS minus VTH square. So, that is equal to 2 milliampere. In fact, with this we can also get GM of the transistor it is 2 milliampere per volt. Earlier we have done this calculation, and we can assume that the lambda is very small. So, we can say that R naught or RDS is very high, we may consider this is very high. So, the voltage gain from gate to drain of this amplifier it is GM into RD with a minus sign, and that is equal to 6. So, we got voltage gain from here to here it is only 6. Now, we can calculate the input capacitance using this information. So, we do have voltage gain it is only 6. So, the C in, part it is we do have CGS which is 10 picofarad, and then CGD 5 multiplied by 1 minus 6. So, that gives us 45 picofarad only. And on the other hand, if we connect the CL here, which is 100 picofarad given here, and if this is 10 microfarad. So, effectively these two together it is giving us 100 picofarad, and of course, we have to consider effect of CGD, and so this is CGS. So, effect of CGD it is coming here almost as is. So, we can say that C out it is equal to CL plus CGD approximately, right. And so, that is we can say it is equal to 105 picofarad. Now, based on this information, of course, we need to know the input resistance here R in, and gate to source resistance of coming out of the device it is very high. So, input resistance it is coming from the bias circuit only, and also we consider the source resistance to get the effect of C in, and the source resistance it is given here, it is 750. So, R in now it is R 1 in parallel with R 2. So, that is equal to 2.25 kilo ohm. So, we do have R in is equal to 2.25 kilo ohm, then R s is 750. So, the first pole, let me use different color here. Yeah, first pole P 1 coming due to series connection of R s and R in, and C 1 it is here, C 2 it is here. So, this is 2 pi, then R s in series with R in multiplied by C 1. So, that is equal to 44 by 7 into we do have together series connection of R s and R in, it is actually 3 k, and then C 1 it is 10 to the power minus 5. So, that gives us the lower cutoff frequency of this circuit, it is even lower than the previous case. So, this is equal to 5.3 hertz only. So, we got the lower cutoff frequency, it is coming here. Then P 2, if you consider P 2, which is 1 by 2 pi, then R s in parallel with R in, and then multiplied by C in, and C in it is only 45 picofarad. So, this is equal to 1 by 44 by 7 into. So, these two coming in parallel. So, that gives us let me check in my calculation. Yeah. So, this is R s is equal to point, or let us say 750 in parallel with 2250, and then 45 picofarad. In fact, this is becoming quite high, particularly the capacitance it is low. This is equal to 6.28 megahertz. So, note that the value of this capacitance it is higher, lower, that makes this P 2 it is higher. Now, let me also calculate P 3, which is coming from R d, the output resistance here. Let me use this space here. Okay. So, we do have 2 pi here, and then R d, and then C out. In fact, if you consider the corresponding numerical value here. So, this is 44 by 7 into R d, it is 3 k, and then C out it is, so this is 3 k, sorry. C out it is 105 picofarad, and in fact, this is becoming 505 kilohertz. Now, this is the case where what we are getting is that this frequency it is lower than this one. So, naturally the upper cutoff frequency it will be decided by P 3, of course, lower cutoff frequency it will be decided by P 1. Okay. So, this is the example where I was talking about that this P2 it is not defining the upper cutoff frequency, it is rather P3 the output node pole, it is still defining the upper cutoff frequency. And then what is the mid frequency gain? We do have the gain of 6 that need to be multiplied by the attenuation coming from R s and R in, and the attenuation there it is of course, that is 0.75, and we do have the input resistance, it is 2.25. So, overall gain A V overall equals to, we do have minus 6 multiplied by 2.25 divided by 2.25 plus 0.75. So, this part it is becoming 3 and yeah. So, this is minus 6 into 2.25 divided by 3. So, that gives us minus 4.5. So, the mid frequency gain it is only 4.5, and the lower cutoff frequency it is 5.3 hertz, upper cutoff frequency it is 505 kilohertz. Okay. So, anyway we know that this circuit will be having low gain, but the exercise here what we have seen here, it is because of the low gain the input capacitance it is not so high. As a result, the upper cutoff frequency it is still getting decided by the pole coming from R d and C L or output capacitance. Now, we can do probably one more exercise, which is self biased, but I suggest that probably you can try it out to solve this problem. So, I will be giving little hint to solve this problem. First of all, here again we shall try to find the operating point of the transistor. So, if you consider R 1 of 9.9 k and R 2 it is 3.3 k, again the voltage coming here it is 3 volt. So, we do have the value of this resistance it is 9.9 k and we do have 3.3 k. So, that gives us 3 volt here, and with this 3 volt if you consider that we do have the base to emitter voltage drop of 0.6, in fact that gives us this voltage equals to 2.4 volt. Now, of course, we are assuming that while the base node it is connected here and then the base current it is flowing here, we are assuming that this voltage, the base voltage it is not changing, and in this case it is valid because the internal current here through this resistor R 1 and R 2 before we connect this base terminal, it was much higher than the anticipated base current. So, even after connecting this base terminal, we can see that the V b still it is very close to 3 volt, right. So, once we have 3 volt here, then if we reduce this drop of 0.6, then we do have 2.4 volt coming at the emitter, and then if you consider R e which is 1.2 k, that gives us the emitter current I e equals to 2.4 divided by 1.2, which means that the I e is equal to 2 milliampere. And we can also approximate that this I c is also equal to same. So, that is also 2 milliampere, and then from that you can calculate G m, which is 1 by 13 mho, and then we can calculate R pi, which is 200, beta is 200 divided by GM. So, that is 1 by 13. So, that is equal to 2.6 kilo ohm. Now, the input, so that gives us the input resistance R in equals to R 1 in parallel with R 2 in parallel with R pi. Probably you can check, I think in my calculation it was coming 1.268 kilo ohm. And the voltage gain, of course, the internal circuit voltage gain from base to collector A naught, which is GM into R C, assuming that this emitter resistor it is successfully bypassed by this capacitor C E. So, this it becomes R C we do have 2.7 and then GM it is 1 by 13. So, that gives us a gain. So, this is K of course multiplied by 1000. So, this gain it is coming close to 200, in fact 207.7 with a minus sign. And using this you can calculate what is the input capacitance, namely C pi plus C mu into 1 plus 207.7. I think in my calculation I was getting close to 1 nanofarad, in fact 1053 picofarad, right. So, using this information of say C in and then R in, you can calculate what will be the P 1 by considering the source resistance R s, which is given here. So, P 1 again you can calculate, this is equal to 2 pi R s plus R in multiplied by C 1, and C 1 it is given here, it is 10 microfarad. So, you can find the value of this one. Likewise, you can calculate P 2 and then you can calculate P 3. So, I will not be doing this one, probably you can simply try it out and get the corresponding solution. So, in summary what we have so far we have covered, it is So, in this module what we have covered here, it is basically we have considered a high frequency model of transistor and particularly in presence of source resistance R s, what is its impact on the frequency response of common emitter and common source amplifiers. And what we have seen primarily, it is the change of the lower cutoff frequency and upper cutoff frequency and also the mid frequency gain. This is the main thing we have done, and that has been done by properly calculating the input capacitance, for which we have considered Miller's theorem. So, we have touched upon the basic Miller's theorem, and then we have seen that that theorem it was helping us to calculate the input capacitance C in, which primarily it was defining the upper cutoff frequency. And then also to get the overall frequency response, we also have analyzed R C followed by R C in parallel circuit, and we obtain the corresponding frequency response. So, these two underlying theory, it was helping us to get the frequency response of the CE and CS amplifier. So, we started with analysis and then the expression of the the poles and all, and later in the third part of it we have considered numerical examples and particularly for common emitter amplifier with fixed bias and common source amplifier in detail, and we have given a hint of how to do similar kind of analysis for common emitter amplifier having cell bias arrangement. I think that is all I do have. Thank you for listening.